Hello, everybody, and thank you for joining us today. Before we begin, I'd just like to have a quick review of the hardware debug architecture that's available on these Cortex-M processors. When people first come to these devices, they often think that the debug interface is JTAG. Actually, it's a proprietary architecture from ARM called CoreSight. This provides a lot of the standard low-level features that you'd find in a JTAG debugger. So you have run controls so we can single-step start and stop the processor. We can also set hardware breakpoints, and we can view the memory, both the peripherals and the SRAM and flash memory. However, within the CoreSight architecture, we also have a number of real-time trace units as well. So there's a data watch trace. So this allows us to stream out reads and or writes to memory locations and peripherals non-intrusively as the code is executing. There's also an instrumentation trace. This allows us to add printf style debug comments to our code. So these can be routed up to the console window in the debugger. So this is very good for software testing, but also for printing runtime messages to yourself as the code is executing. And again, this can allow you to gain an insight into what's happening in the code as it executes. Then there's an additional trace unit that's an optional fit that can be found on a number of processors. And this is the embedded trace macrocell. This takes up a number of additional pins, but allows the microcontroller to stream out every, every instruction as it's executed to an appropriate hardware debugger, so we can build up an instruction trace, so we can see both how our code executed and also gain a lot of timing information from it. Now, the basic CoreSight connection is 2 wires as opposed to the JTAG 5-pin connection. So this will allow us a basic run control type debug interface. We can also enable an additional pin called the serial wire out pin, and this is the pin that supports both the instrumentation trace and the data watch trace. Now, by default, the basic 2 pins, the serial wire debug pins, are available for debug, but depending on the silicon vendor, the serial wire out pin may be multiplexed with other peripherals or GPIO. So this can introduce a bit of confusion when trying to configure it. And again, we'll look at an easy way to set this up later on. Similarly, the ETM pins are generally multiplexed with GPIO, so we need some additional support to enable those if we're going to use the instruction trace. In terms of debug adapters, ARM has published a block of firmware called CMSIS DAP that allows any Cortex-M microcontroller with a USB interface to be converted into a CoreSight debugger. So this allows manufacturers to put very low-cost debuggers onto evaluation boards, and then you can simply plug into that board via a USB cable, and then you can connect your development tool and start debugging. And this is a very effective way, and it works very well. It's a bit bandwidth limited, so while it supports a lot of the more advanced features, it tends to choke a little bit when you're trying to get lots of data out. But it gives you really a zero-cost debugger. So using the CoreSight architecture really starts at free. However, to get the real performance out of the debug architecture, ARM produce a number of ULINKs. These are hardware debug adapters, which provide various levels of debug support. So at the top, we have the ULINK Pro, which provides high-speed debugging and also instruction trace. ULINK Pro D, which provides high-performance debugging, but does not have the instruction trace. The new ULINKplus provides good bandwidth, so we can get a lot of data off of the board, and it also allows power analysis, and it contains an integral logic analyzer as well. And again, we'll look at this in more detail later. And then for entry-level debugging, there's the ULINK 2 that was released, I think, in about 2006, that provides the basic CoreSight debug features for all Cortex-M microcontrollers. Now, the other thing to be aware of is when you're designing your hardware board, a lot of evaluation boards are still fitted with this large JTAG style connector. So this takes up a lot of board space and brings out all of the pins for both the serial wire debug and also JTAG debug. If you're designing your hardware, it's important to note that there are a number of much smaller connectors that have been specified for CoreSight debugging. So these just bring out the necessary serial wire debug and serial wire viewer pins. So if you're developing with new hardware, then you should fit these smaller connectors. So there's a 10-pin connector, which gives you the basic debug connection. If you want to use instruction trace, then there's a larger 20-pin connector that brings out the ETM pins. It's also important to be aware that when you give this information to your hardware designer, he'll always put on the smaller connector. So if your microcontroller has the embedded trace macro cell fitted, do specify that you're going to put on the larger socket. The 10-pin connector maps onto the 20-pin connector. So by putting the larger footprint, you can still use the basic 10-pin connection. But if you only have the smaller connector and you get into problems later on, it's then not very easy to connect a trace tool, which is very useful in sorting out problems. So at least put the footprint for the 20-pin connector on. First of all, we'll have a look at the streaming trace. So as I mentioned, certain Cortex-M microcontrollers can be fitted with the embedded trace macro cell, the ETM. This is an optional fit, which has to be designed in when the silicon vendor designs the chip, and is only available on Cortex-M3, M4, and M7. If it is fitted, then you will need an appropriate hardware debug tool. So in our case, this is the ULINK Pro, and it's then possible to have a streaming trace. So this, rather than buffering data within the ULINK Pro, it streams every instruction as it's executed directly down onto your hard disk. So then we can analyze all of the data, and we've effectively got a trace buffer that's the size of your hard disk. So gigabytes of trace, we can capture everything. So this means that we can get a detailed instruction trace, both at timing, assembly level, and also C code. But once we have that information, it's possible to provide additional debug views. So code coverage, we can validate every line of code that's been executed. Performance analysis, we can get runtimes of all of our functions. And also we can look at more detailed timing information within the editor view as well. Now the ULINK Pro is specified to run at CPU, the Cortex-M processor clock speed of 200 megahertz. However, in practice, a lot of the silicon manufacturers, the pins that bring out the trace information aren't fast enough to support this speed. So very often we find that the trace, the ETM trace, tops out at around 160 megahertz. So if you are designing a project and intend to validate code with the trace, you need to be aware, do some preliminary testing, or be very careful with your board layout to get the maximum trace speed. On the Cortex-M0+, ARM introduced a different style of trace buffer, and this is called the micro trace buffer. This allows you to take a bit of the user internal SRAM of the microcontroller and convert this into a circular snapshot trace buffer. So now as your application code is executing, it's being recorded into the RAM used by the micro trace buffer. And then when you stop the execution, you can download the contents of that trace buffer and display it within the development tool. So this gives us a very useful debug utility so that we can run our code. If we have problems or we want to analyze a section of the code, we can get a snapshot of its execution and look at it within the development tools. And this trace buffer technique is also available on the newer Cortex-M23 and M33 processors. So going forward over time, all of the new generation of Cortex-M processors will have the possibility of this extended internal trace buffer as well. There are some other Cortex-M3s, M4s that have a different form of trace buffer called the embedded trace buffer, ETB, which is another style of trace that effectively does the same kind of thing but has its own dedicated SRAM. So there's a number of styles of instruction trace, but over the next few years, as we get the new generation of Cortex microcontrollers, having on-chip trace is going to be a huge benefit to debugging and testing code. Now, within the debugger, there are a number of ways of customizing the debug view depending on the microcontroller and the software that you're using. So we have views to look at the custom peripherals that a manufacturer's added. We have ways of looking at variables within a software library in detail with a component viewer. And we can also send real-time application information to ourselves with an event recorder as well. And there's also a comprehensive scripting language that allows us to extend our debugging to do testing and code validation. So we'll have a look at how all this works over the next few minutes. Now, when you're working with a specific microcontroller, in most debuggers, there is a set of windows that will allow you to see the current state of the peripherals that are within the microcontroller. And as the number of Cortex processors started to increase, developing these windows really became a bit of a bottleneck for all the people making debuggers. There may be something like 10 to 20 windows within a given microcontroller, and then many, many different variants. So they became quite an issue to actually develop them. So as part of the CMSIS standard, there's now a software standard called the System Viewer Description file. And effectively, this is an XML file that describes the layout of a given peripheral and the construction of these windows. So these XML files can be generated by the silicon vendors and then imported by different debuggers to create these peripheral views. So this greatly speeds up our ability to provide support for new devices so that when the silicon is actually released and available to customers, all of the peripheral support within a debugger should be ready to go. Again, so you're not on the bleeding edge waiting a month or two to get proper debugger support. Now, within the Keil toolchain, this idea has been extended somewhat in the form of a component viewer that does the same thing for software libraries. So here we can generate a view that looks into a software library and can take the key variables inside that library and display them in a meaningful way. So the view here is looking at an operating system. We can see into the state of all the running threads, into their task control blocks to see exactly what state those threads are in, and any other objects that are within the operating system. So these within the Keil tools are available for the RTX operating system, but also all of the Keil middleware as well. And they're very, very useful to see exactly how the software is executing. Now, these views are made in a similar way to the peripherals in that they're constructed from XML files. So here we have an example of a component viewer XML file. So the top half is used to describe the symbols and the data, and then the bottom half is used to lay out the window with those symbols. So these views we can make for ourselves, and it's relatively straightforward and a quick job to set up a basic view. So as you're writing and developing your application, over the lifetime of the project, you can start to build these component views which take probably a couple of hours each. And then within the debugger, you can get a detailed view of the key variables that are in your software. So these allow you to look at the variable, but also expand it in terms of any internal flags and fields that are inside it. And time spent here early in the project really does help you debug the code later on. So it's relatively straightforward to do. Once you've developed the XML file, we can then go into the debug window, press the Manage Component Viewer Description Files button, and then import our new description file. That will then be available within the debugger every debug session that we go into. So adding component views is a nice, easy way to customize your debugger to provide much more detailed debug information and speed up debug sessions as well. There is an application note available on the Keil website that talks you through how to construct one of these component viewer files, and it also makes a useful stack analysis utility as well. So again, that's probably worth looking at just in its own right. Within the pack installer, if you select the devices tab and then the ARM section, inside the examples, there are also a range of these system viewer description file examples as well that demonstrate how to construct various levels of complexity on these screens. To get access to the instrumentation trace, we can redirect standard out. So whenever we do a printf, we can redirect it to the instrumentation trace. So within the runtime environment manager, in the compiler section, there's a subfield called IO, and here we need to enable the standard in, standard out, and we can switch those over to be routed to the instrumentation trace. This will add a support file to our project that takes the putchar, getchar from printf and then redirects it to the instrumentation trace. So it's very easy to convert the software to route debug messages up to the debugger. However, in the debugger, we also need to enable the instrumentation trace, and this is done by first setting the core clock frequency to match the CPU frequency that's running on our target. So this effectively sets the baud rate for the instrumentation trace. And then we have to enable the instrumentation trace itself. So the instrumentation trace has actually got 32 channels, so their different information can be sent to different services within the debugger. But the public channel, which uses printf, is instrumentation port 0. So we need to tick that box and also enable the privilege box as well. So now when we run printf, we'll route that to the console window that's within the debugger. And very often in our own projects, we use this as an interface to a lightweight testing harness so that we can easily validate or quickly run software tests over new code within the project before handing it over for formal testing. That's proven to be quite a good way to work. One of the things that does catch people out is that the instrumentation trace and the data watch trace use this additional serial wire out pin. On some manufacturers, this may be multiplexed with GPIO, so nothing works until we configure the serial wire out pin. This used to be done by adding scripts to the debug window. However, in recent releases, there's now a new tab called the Pack tab, and this has integrated the scripts directly into the debugger. So when you select a specific device, scripts appropriate to that microcontroller are now automatically added to the debug toolchain. So this does make life a lot simpler. So here in the Pack tab, we can then go in and open up the debug script and view this and set any custom features for that microcontroller. So for example, enable a serial wire out pin, configure how the CoreSight debug architecture behaves in low power modes, etc. Some manufacturers allow you to freeze things like timers or serial interfaces so that it stays in step with the debugger as well. So when you're configuring, have a look in the Pack tab and have a look into the debug configuration script file to see what options are available to you. Again, this is quite important when you first do your first Hello World project. Now, the instrumentation trace is a way of getting information off of the chip into the debugger as the code's executing. In later releases of the software, there is a second way of doing this called the event recorder. Now, while the instrumentation trace is available on the Cortex-M3, M4 and M7, it's not available on M0 and M0+. So on the smaller devices, you don't have the more advanced trace features. So this second technique, the event recorder, is available and can be used on all Cortex-M micros. So this greatly improves the debug experience on M0, M0+. So this is using a technique that's similar to the micro trace buffer in that we're adding some debug software to our code, and this is writing to a memory buffer that we've created inside the chip. So this is intrusive as the code runs, but then the debugger, the hardware debug adapter, can read the logged data and copy that up to the debugger non-intrusively on all of the Cortex-M microcontrollers. So here we have to enable the event recorder, again within the compiler section of the runtime environment. So here we tick event recorder, and then in the standard out box, we can change from using the ITM to using the event recorder. So now when we use a printf command, it will write into the event recorder and then be copied up into the debugger and displayed in the console window. So again, this is extremely useful when you're working with an M0, M0+. So the event recorder, once you've enabled it, if you're using the operating system, we can then start it automatically within the RTOS configuration file. So here we switch on the event recorder global initialization and then tell it to start working when the operating system kernel begins. If you're not running using an operating system, then there are bare metal functions that allow you to start and stop the event recorder manually. So it's available whether using the operating system or not. Now, while we can use the event recorder simply as a printf channel, It's also possible to add annotations to our code so that we can send detailed debugging messages up to an application trace window called the event recorder. So here we have the annotated operating system. So as that executes, it's sending small amounts of information up to the debugger, and these are then being expanded into more detailed debug messages and displayed within the event recorder. These are fairly structured messages, so we can apply a lot of filters to enable and disable different groups of messages from either the operating system, the middleware, or our own code. So this allows us to get very detailed views or just get a few error messages if something's going wrong. So again, these messages can be expanded by extending the information in the system viewer description file. The component viewer description file. So where we created our component view, we can now add messages that expand our event annotations. So here we're describing the ID of the message, some filtering information, the debug message that we want to give ourselves, and if it's carrying any data, we can take that out and format it to be displayed in a readable form as well. So from the event recorder, we're sending a minimal amount of information, and then this is interpreted on and expanded within the debugger to provide detailed debug information for us. And again, this isn't a great deal of work to add, but once you have, it pays off later as you get more complex software or complex problems later on. So then in our application code, we've got various event recorder macros that we can add. So here we can put out the ID and any associated data that we want to send with that message. We add these tags into our code. Then as it runs, these will start to appear in the event recorder within the debugger. And again, there's a number of simple examples within the pack installer that you can see how this is structured and start to create these event annotations for your own code. These event annotations, as well as providing debug information, they can be used to perform timing analysis as well. So there's a separate window which allows us to set up the event recorder and start and stop the timing statistical analysis from running. So here we can then get max, min, and average run times between these different event recorder annotations. So you could do this on entry and exit to a function, and then you get its max, min, and average run times. And this can be done on every Cortex-M processor. So this gives us a lot of timing information and validation of our code as well. And we can have up to about 64 of these slots, and these are all then displayed in our event statistics window. If you're using the operating system, there are also a couple of additional tick boxes that are useful within the thread configuration. Here we can do stack overrun checking. This places a sort of a magic number at the edge of the stack space of every thread. So if the thread overuses the amount of memory allocated to it, it will automatically take you to a trap within the operating system. So you can see that your code has overrun the memory allocated to it. There's also a stack usage watermark. So this places a pattern through the stack space of the thread allocated memory. And then as the code runs, we can see how that watermark has been changed. So this allows us to see the high watermark, and also how the runtime usage of that stack varies as the code's executing. So this again gives us quite useful information into how the memory of each of our threads is being utilized, and we can then optimize our code from there. An important new feature that's been added to the debugger in the last release or so is the system analyzer view. This brings together a lot of the real-time information and displays it graphically within the tool. It allows us to gain a very detailed insight into exactly how our code's running. So there's a lot of information in this screen, and starting at the bottom, if you're using the operating system, you can view the execution of all of the threads. So here we have a view that shows the runtime of each thread, how often they occur. It's also useful to look at the amount of time being used by the idle thread as well. So that gives us a very good idea how much spare processor time we have on our processor. Above that, the event annotations are also displayed in the system analyzer. So again, if you're looking at detailed application information within your code, you can see directly when events occur. Above that, we can have the same runtime view, but this time of all of the interrupts within the system as well. So we can see exactly how those are interleaving with the operating system threads. These are picked up from the performance registers that are within the CoreSight debugger. So the information about the interrupts is non-intrusive. We're not losing any time seeing that. The information that we gain from the threads is sent up through the event recorder or the ITM. So the thread information is a little bit intrusive on the processor. We can take also information from the data watch trace, as well as putting that into a watch window. We can put it into the system analyzer so that we can gain a graphical view of exactly how the data in a variable is varying over time. When I first came to this, it was quite a sort of a graphical thing to show people at seminars or during demonstrating the code. But when I first used it in a DSP project, it was an extremely valuable and useful tool. You could see the shape of the data, you could work out, see the actual filtering of data, etc. So it's, again, a very, very useful view to get familiar with. If you're using the ULINKplus, we can also record the current and voltage of the microcontroller directly into the system analyzer as well. So we can relate its energy usage back to the code execution as the code is running. And then finally at the top, we can see the frequency that the CPU is running at. So again, when we do our first Hello World program, we can make sure that we've set up the debug clock tree correctly, and we're getting the processor running at its maximum speed. But also, if we're dynamically changing that clock during runtime, we can see the effect of that as well. Now, as I mentioned, the ULINKplus has the ability to measure the energy usage of the microcontroller. So here, as well as the CoreSight debug interface, we have a power interface which we can connect onto any power region that's on our development board. This can either be plugged directly into the ULINKplus, or there are a number of shunts that are available so that we can easily scale the voltage range. And then as the code executes, we can record the current and voltage directly into the system analyzer. So this can be, again, very useful, obviously, if you're developing low power application, but it has been used to demonstrate or show sort of weaknesses in hardware as well. So again, it's useful in multiple ways. Once we've started to record that information, we can also add it to the event statistics view as well. So where we're using the event recorder to gain runtime information, we can also see the energy usage between different events in our code as well. So we can go down and start to look at different regions, different functions in our code, and see how efficiently those are running, and if possible, optimize them. The ULINKplus also has a 9-channel logic analyzer as well. So this gives us digital I/O and also analog I/O as well. So we can output and stimulate hardware, and we can also see the state of external signals as well. This is both directly through a window within the ULINKplus debugger, but the logic analyzer is also available via a scripting language within Microvision. So we can start to write test scripts either to output, for example, in this case, we're toggling pins, or we can generate analog signals onto a board, or indeed we can measure outputs from our hardware as well. So this allows us a way to do in-the-loop testing. And again, would suspect that the Microvision tools will be extended to support more testing features in the near future. And then finally, there are increasing numbers of multi-core Cortex processors, multi-core Cortex microcontrollers. Often these will have Cortex-M4 and an M0, or increasingly Cortex-M33s are found on devices. So here it's possible to connect one of our hardware debug adapters to our hardware, and then we can have multiple sessions of the Microvision debugger connected to that debug unit and controlling the individual processors inside the chip. Now we've done a couple of projects using multi-core microcontrollers, and it works, but you have to be a little savvy about how the hardware is constructed underneath. There also you have to generally follow a sequence to bring up both processors correctly. So there's a bit of synchronizing and managing both of the underlying devices, but it does work and it's achievable. But do go in with your eyes opening when you're going to use a multi-core processor. So I think that's covered a lot of what I wanted to talk about this morning. As I said before, if you have any questions, please raise them and we'll get back to you on email. This talk will also be available as a video which we uploaded to our website if you want to go through any of it again. Or if you have a general question, just email me directly on the email address below. So thank you very much for your time this morning, and I hope you found it useful. Thank you and goodbye.